We're starting a new chapter here to discuss gases. Many important substances exist in gas forms. For example, we need oxygen gas to live, and we're surrounded by air, which is a collection of gases. In order to understand gases, we first need to know some of its basic properties. The first is that gases don't form specific shapes. Instead, it just fills the container that it's placed in. Two properties of gases are very easy to observe. A gas will fill up the entire volume of a container by exerting pressure equally in all directions of the container's walls. Look at this balloon that is being filled with a gas. It immediately expands in all directions due to the gas pressuring the skin of the balloon. The gas is everywhere inside the entire balloon. Despite filling an entire space, gases are very compressible. Look at how easy it is to press down and change the shape of the balloon that's completely full of gas. Gases also have very low density. This can be visualized easily when we see water vapor bubbling to the top of liquid water. The gas has a lower density than the liquid, so it rises to the top. Lastly, gases mix easily with other gases. The air around us, for example, have a mixture of many gases, with nitrogen and oxygen being the major components. All of these observed properties of gases can be explained using a theory of molecules that's called the kinetic molecular theory of gases. This theory was developed through experimentation and hypotheses of a large number of scientists over a few hundred years. Before we get to this theory, though, let's first discuss the observations that lead to the theory. The first observation about gases is that there are three easily measured properties. The first property is pressure, with the symbol P. Pressure is force per unit area. There's often confusion between the concept of force versus pressure. The difference between force and pressure can be illustrated by the picture shown here. Force is the amount of mass multiplied by the acceleration due to gravity. In the picture shown here of a ballerina in three different poses, the force applied by the ballerina on the ground is the same. This is because the force depends on her mass and gravity, which are unchanged in the three poses. The pressure differs in the three poses based on the area that she's applying the force on. If she's standing on both feet, then the force is distributed in the entire area of the 2 feet. If she's standing tippy-toe on both feet, the area is smaller, but the force is the same, so the pressure is higher. Lastly, if she's standing on one toe, then all the force is channeled through a very small area, so the amount of pressure is very high on the area of that one toe. No surprise that ballerinas often break their toes due to these high pressures. The pressure of the air around us, which we call the atmosphere, can be measured using a barometer. There are several units of pressures. Atmospheric pressures are measured in units of ATM, or millimeters of mercury, or torr, which is short for Torricelli, the person who designed the first mercury barometer. Other common units of pressure are pounds per square inch or Pascal. The conversion of these different units of pressures is shown in this table. The way you read this is that 101,325 Pascal is the same as 1 ATM and 760 millimeters of mercury, and so on. These are all values of air pressure at sea level. As we go higher in altitude, the amount of air particles decrease, and so does the air pressure. For example, this graph shows that the pressure at sea level is 101.3 kilopascal, while at the top of Mount Everest, the pressure is only 33 kilopascal, about one-third the value at sea level. This tells you that there's a lot less air, and therefore much harder to breathe, on top of Mount Everest than at sea level. Another important property of gases is its temperature, with the symbol T. Gas temperature is measured in units of Kelvin. As a reminder, you can convert the Celsius temperature to the Kelvin temperature by using this equation. The last property of interest for gases is its volume, with symbol V. A gas can be placed in a constant or variable volume container. A constant volume container doesn't change its volume despite the amount of gas that's added. An example is a steel box or a classroom. A variable volume container can change its volume as more gas is added. An example is a balloon or a tire. Volumes are typically measured in units of liters. For over 100 years, people have studied gases and observed specific relationships among the three properties of gas: pressure, volume, and temperature. These relationships are now written as equations which we call the empirical gas laws. Each law is a name for the scientist who discovered it. We will start discussing these laws chronologically. In the mid-1600s, Robert Boyle discovered that for a fixed amount of gas kept at a fixed temperature, P or pressure and V or volume are inversely proportional. What this means is that if the pressure doubles, the volume is reduced by half, or vice versa. The following simulation shows what Boyle observed. Here we have air trapped inside a sealed syringe, so no air can enter or leave the syringe. As the plunger is moved to reduce the volume of the gas, the pressure increases. So decreasing volume results in increase in pressure and vice versa. This is what we call Boyle's law. Interestingly, if we multiply the pressure and volume values that we find, the values turn out to be what we call a constant. That is, the value of P times V doesn't change regardless of the specific values of P and V that we use. Mathematically, Boyle's law can be written as P times V equals a constant. The symbol for the constant is usually the letter C or K. In addition, the specific values of P and V can change, but their product is always the same. So that means we can write P1 times V1 equals to P2 times V2 equals to P3 times V3 and so on, where all of these expressions are equal to the same constant. Calculations for Boyle's law can be done in any units of pressure and volume. All you have to be sure of is that the units for pressure at different conditions are always the same one, and so is the volume. So if your P1 is in ATM, your P2 should also be in ATM. Or if V1 is in milliliters, then V2 must also be in milliliters.
Okay, so let's take a look at this Boyle's law problem. It says a cylinder equipped with a movable piston has an applied pressure of 4 atmosphere and a volume of 6 liter. What's the volume if the applied pressure is decreased to 1 atmosphere? So the situation is originally you have some pressure-volume combination, and then in the end the pressure is changed, so the volume should also change. Now notice that because the pressure is decreased from 4 atmosphere to 1 atmosphere, we would expect the volume to increase because Boyle's law states that pressure and volume are inversely proportional. Let's do the actual calculation. So Boyle's law can be written as P1 V1 equals P2 V2 and solve for the volume in the second condition. So we're going to divide both sides by P2 so we can isolate our V2, and that would leave us with V2 equals to P1 V1 over P2. In this case, our P1 is just the pressure in condition 1, which is 4 atmosphere. Our volume 1 is 6 liter. Our pressure 2 is 1 atmosphere. And notice that that gives us 24 liter as our answer, which is matching our prediction because volume should increase when pressure is decreased.
A second empirical gas law was discovered by Jacques Charles, a French inventor who lived in the late 1700s. He realized that when a gas is heated, its volume will also increase as long as the pressure and amount of gas are held constant. Charles was also known as the first person to travel in a balloon that is filled with hydrogen gas. Charles's law can be shown using the following simulation. Notice how the volume of gas decreases when the Kelvin temperature of the gas is decreased. Similarly, notice how the volume increases when the Kelvin temperature of the gas is increased. If you divide the volume by the Kelvin temperature, you will find that you get the same value every time. This means that Charles's law can be written in the following equation form. V over T equals a constant. Using the same idea as we did in Boyle's law, that means we can write V1 over T1 equals V2 over T2 equals V3 over T3 and so on. It's important to remember that Charles's law is only observed when the temperature is in degrees Kelvin.
So let's take a look at this Charles's law problem. It says a sample of gas has a volume of 2.8 liter at an unknown temperature, and when the sample is placed in ice water at temperature equals 0 Celsius, its volume decreases to 2.57. So the question is, what's the initial temperature? Okay, so we can start with the Charles's law relation relationship, which is V1 over T1 equals V2 over T2. We notice that we have an initial volume, so that could be our V1. We have some initial temperature that we don't know, so that could be our T1 that we're trying to solve for. We have a second temperature that we know, which is T2, and we have our second volume, which is V2. To solve for T1, we're going to need to do a couple of steps. Algebraically, we can multiply both sides by T1. That would cancel this out and allow us to have our T1 on one side. And notice that we're trying to solve for T1, so we have to isolate all the other variables to the other side. That would require us to multiply both sides by T2. That would cancel out T2 on this side, and then to divide it by V2, which then allows us to just have T1 on one side and then everybody else on the other side. So just to clean this up a little bit, T1 would look like T2 times V1 over V2. Now, the other thing to note is that temperature in gas calculations must always be expressed in degrees Kelvin. So our T2 is 0 Celsius, which is the same as 273 Kelvin. Once we have that, it's really just a matter of doing some calculation. 273 Kelvin times V1 over V2. And when you do this calculation, what you get is 297 Kelvin. Now, if you want your answer to be in Celsius, you're going to have to subtract 273 out, and that would give you 24 degrees Celsius.
The third empirical gas law is named after Joseph Gay-Lussac. He noticed that when the volume and amount of gas are kept constant, the pressure increases as the temperature of the gas increases. The following simulation shows the increase in pressure as the gas is being heated. Gay-Lussac's law can be written as P over T equals a constant, or alternatively, P1 over T1 equals P2 over T2 equals a constant. Just like in the case for Charles's law, the temperature must be expressed in degrees Kelvin for this relationship to work. In the empirical gas laws we discussed, we see the specific relationship between two of the three gas properties, P, V, and T. We can write a more general equation, which is called the combined gas law, for all the three properties as follows. P times V over T is equal to a constant for a given amount of gas. Alternatively, we can write P1 times V1 over T1 is equal to P2 times V2 over T2 for a given amount of gas. Note that for these laws, the relationship is for a fixed amount of gas. So you can't let gas in or out during the experiment if you want to observe this relationship.